The purpose of this meeting is this webinar is based on the idea that this community has begun to think about how the Earth surface and environmental sciences community can better collaborate to address science and societally relevant questions. And so this webinar is meant to inform the greater community as to where CZO network stands today. Before I introduce the webinar, I just want to point out to whoever's signed in that week at AGU, the CZOs have a pretty good. If you're interested in looking at a list of all the 150 or so presentations that are coming out of the observatories, just go to the criticalzone.org website and you'll see under events right in the middle of the screen, you'll see a URL that'll take you to a list of abstracts. We'll have a 2521 in the exhibit hall. We're having a town hall on Tuesday at 12:30 to 1:30. There will be food and beverages available. That's in Moscone West, room 2005. And in addition, for the graduate students and postdocs who may be logged in, there will be a social at the Bin 55 restaurant and bar in the Marriott on Wednesday from 4 to 7. So I'm going to turn it over briefly to Dan Arthur, who's going to describe some of the rules of engagement for this web, and then I'll introduce our speakers.
Good morning, everyone. I'm Dan. I'm running the technical side of the meeting here for Tim. And, just a couple of administration issues. When you call into the audio portion of the conference, could mute your phone. And if you have questions through the presentations, I will be monitoring the chat window, so please put them in the chat. Then after each presentation is done in turn, after they're all done, we will do a more of a discussion where Tim will read off the questions, and we'll sort of go from there. So anything else, Tim?
Nope, that'll do it.
Okay, I'll turn it back to you.
Pop up the next slide. Okay, so the title of today's webinar is Using a Critical Zone Observatory Network to Explore the Architecture, Dynamics, and Evolution of the Critical Zone. And the way this is organized is we're going to begin with an introduction from Enriqueta Barrera, who's our program director at the US National Science Foundation. That will follow with a portion of the talk focusing on the CZOs and what they are and generally what they're about, and that will be by Sue Brantley from Penn State. She's also the PI at Shale Hills. Bill Dietrich from UC-Berkeley, Eel River PI, will describe to us his effort to draw together a series of cross-observatory science questions. And then finally, Jon Chorover from the University of Arizona, Santa Catalina-Jemez PI, will talk to us about how the U.S. observatories have organized measurements. After that, we'll have a question and answer period that could last up to 20 minutes if needed. So, Enriqueta, are you ready?
Yes.
All right.
Okay, good morning. My name is Enriqueta Barrera, and I manage the Critical Zone Observatory program along with some of my colleagues at NSF. This is the Division of Earth Sciences. In the talk today, I will describe some of the key components of the Critical Zone Observatory program, and then present some opportunities to be involved with the observatories and that we call the CZOs. Okay, the Critical Zone Observatory program is really a community-driven effort. I'm sorry, I just got... Okay. It's a community-driven effort. The need for a program of environmental observations using approach was articulated by the geoscience community more than a decade ago, and NSF then responded to make this happen, to the need. So the CZO program is composed of individual sites that are pursuing their own questions. The sites also form a network that are pursuing questions, and you're going to hear about this today. So the critical zone science is a new science. I mean, that's the perspective that integrates a mechanistic of physical, chemical, and biological processes that give the form and function of the Earth's surface layer that we call the critical zone. So therefore, if you are a biologist and you're interested in how a biological process interacts with hydrogeochemical, you should look into the work that is being done at the CZOs and see whether you will be interested in establishing relation. One very important point NSF was very proud is that the CZO program was created to be a facility for research and for the broad surface Earth community. And so as such, the CZO network will host science for going backwards here. So the program was grown from 3 sites that were founded in 2007 to 6 sites in 2009, and then the 6 sites were recompeted in 2013, and from that competition, 4 new sites were added, and now we have a total of 10 sites or awards. Some of the sites are co-located with those of other organizations and government agencies such as the LTR, NEON, the Forest Service, or the Department of Agriculture, ARS. So I often get asked, when will there be the next CZO competition? And the present awards that we have now started in 2013 are for 5 years. So therefore, the answer is we don't expect to have a competition in the near future. The best source to obtain information about the CZO sites and the program is the website. This is criticalzone.org. At this website, you can find information about each of the sites. You can see it here. And you can also find information in relation to research, the infrastructure, the data, publications, educational outreach, and also people who is involved and who to contact. From the statistics that we have of this of the website, data seems to be the most popular item, and there are 217 data sets that can be accessed here. So the CZO sites must make their data available to the community at large and to the public via this website. A very important goal of the CZO program is to train the next generation of in this new interdisciplinary science. And at the 10 CZOs that we now have, there have been 110 graduate students at present, and already about 42 have graduated. Likewise, a good number of undergraduate students have been part of the program. For graduate students inside and outside the CZO program, there is the opportunity to apply to the EAR fellowship program. This is a postdoctoral fellowship program, and this CZO program has greatly benefited from this opportunity since there have been several fellowships that have been awarded for both site-specific and cross-site research. A more successful opportunity is also the CZO International Scholar Program. In 2007, there have been 54 graduate students within and outside of the CZOs from about 16 universities throughout the United States who have visited more than 20 European host institutions and field sites. So this program is expected to continue, the International Scholar Program is expected to continue through 2019. Then we also have for undergraduate and teachers, the Christina River Basin and the Shale Hills are jointly running this, what is called the RET program. And this is a summer program for undergraduate and teachers, as I mentioned before. It places 6 undergraduate students at each of the 2 sites, and this program will continue through 2016. It's expected to continue through that time. So another component of the CZO program is a recently created national office. This is the CZO-NO. The national office has 2 broad functions. One is to coordinate the research and education of the activity of the network of sites, and the other one is to be the point of communication of the network with the large science community and the public. So if you need information or if you have a good idea for organizing a workshop on a cool, please contact the national office. These 3 persons here, Lou Derry, who is the PI of the war, and also Robert Ross, who is involved with the outreach and education. So these are, one of them will be able to advise you or to point you in the right direction. So you may be asking, how do I become involved with the CZOs? Well, there's a number of ways that you can do that. I'm just listing here a number of those, and I will say that some of the CZOs have seed grants, and that I know of, Linkages, Southern Sierra, and Shale Hills have seed grants. These are to start a small-scale project at one of the sites, and please contact the PI of the site. Made a proposal to one of the programs at NSF, the programs in the Surface Earth Processes section of Earth Sciences. The research programs in the sections are Geomorphology and Land Use Dynamics, Geologic Sciences, Geobiology and Low Temperature Geochemistry, and Sedimentary Geology and Paleobiology. These programs will co-review proposals that cross boundaries, and this program will also co-review proposals with the ecosystem science in the biology directorate of NSF. In fact, in the past 4 years, this program has provided about $2.5 million for projects at CZOs for researchers that are, in fact, outside of the CZO program. So this is a very good source. There is, I will highlight, there is a graduate research group that is organized by postdocs and graduate students, and the South Korea is a very good source of information if you're a graduate student or a postdoc. It's led by Nikki West. Here is her contact information. The sites organize workshops and ask to find out when they will take place. Every 2 years, there is an all-hands meeting, and the next one is going to be at Shale Hills in 2016. These events are usually announced on the website and ask the national office for the upcoming, or you can ask also the national office for the upcoming events. And they're announced, of course, on the website. In summary, there are multiple ways to become part of the CZO program. And please let the PIs or the national office know how you would like to be involved. So in closing, I would like to point out that the CZO program has a strong international dimension. Since before the creation of the CZO program in 2007, the US Critical Zone science community had been working with the European scientists in a parallel effort to create sites, observatories in Europe and elsewhere. And this slide, I just listed here a number of the programs that currently exist that are akin to the critical zone. And these are parallel efforts going on in Europe and also in China. So it is expected that these initiatives in international initiatives and others will provide further opportunities for establishing international collaboration. So keep your look over and see what is on the website and ask questions if you want to know what is going on and you haven't gotten the information right away. But there are a lot of things going on with the CZO program and many opportunities for scientists and students to get engaged. So this is all I have to say from the side of NSF. And I guess I will wait later to answer any questions you may have.
Just a quick reminder, if everybody on the phone could make sure your phone is muted unless you're one of the presenters.
Okay, so the next part of our talk will be from Sue Brantley. Sue, are you ready to screen share?
I'm ready, but I'm still seeing the last slide from Enriqueta's talk.
I'm going to stop sharing.
There we go. Do I need to switch my monitors? Am I sharing the right monitor? Is my slide up?
I see your slides.
Okay. So there's some overlap between my talk and Enriqueta's, and I'll go a little bit faster through those slides where there's repetition. But what we'd like to do, Bill, Jon, and I, is just talk about the network and think about it as a way to explore architecture dynamics and evolution of the critical zone. So I'm just doing the intro. Really has been focusing on cross-site questions that are emerging, and then Jon will be talking about common measurements. So just to remind you, we think of the critical zone as the part We think of the critical zone as the part of the Earth's surface extending from outer vegetation canopy to groundwater. And it's very complex. It's controlled by a network of chemical, physical, and biological processes. And this is just a diagram I've been playing with. This is by my colleagues. And I could put a million more feedback arrows in here. But this is the kind of thing we're grappling with in the critical zone to try to understand. And because of the complexity of biota, Earth's materials, water, sort of meteorological processes, we need scientists across many different disciplines working together and really working across all these different time scales. And we don't even agree about how this diagram should be shown. And I just put up a version of the diagram, which everybody would make a little bit differently, but this was made by a colleague here at Penn State in the Susquehanna Shale Hills CZO, emphasizing the biota. Now, having said that, what we know is that the critical zone is a structure that influences the storage and flux of water, solutes, sediment, biota, and energy, and that by means of those fluxes, the critical zone is absolutely critical because it provides ecosystem services. We're even thinking about the term critical zones. And so it's important that we understand this very complex system, and that's what the CZO program is all about. Three general questions that have emerged from the critical zone observatories that are already in place are shown here, and I'll just throw them up there because Bill's going to come back and talk about these. Looking at properties and processes, looking at how they respond to perturbations, and then looking at how we can understand the critical zone and their properties and processes to enhance ecosystem services. So what is a critical zone observatory? It's simply a location which is chosen and funded where a group of people work together across disciplines to really grow our understanding of architecture, dynamics, and evolution. And this is a magnificent picture from Andy Pike, who used to be at the University of Pennsylvania, of the US CZO. I mean, just simplistically, why does this piece of the planet look the way it does, and how can we understand how it's changing over time? So what we do at CZOs is we measure landforms, we survey biota, we sample, we use sensors, we measure human impact. Sometimes we do perturbations and experiments. And then we take all these measurements at all the different spatial scales and use expertise from all the surface disciplines to try to understand those data that emerge. And the data that emerge are very complex. I call this a flower diagram because we're trying to understand the critical zone at the center, but there's all different kinds of data. There's atmospheric data, there's water data, land surface data, regolith data, biological data, and each of these boxes is something that can be measured. And so this is a kind of an ontology of the kinds of data that are being collected, and it gives you just sort of a hint of the complexity of trying to create a data structure or a data model so that we can place this online. And interesting, some of the data, some of the measurements change very quickly, some change very slowly, and the amount of metadata you need changes across this diagram. And so it's a complex process to get the data online, but that's very important because we want the data to be useful outside of the CZOs and across the disciplines. Finally, with the data, we can then use and develop and test models of Earth's surface processes so that we can understand how the CZ changes due to different forcings, and then how to interpret the record. And it's really important, this crossing of timescales, which I would like to emphasize because it's really what makes critical zone science different than science. What, in effect, we're trying to do is look at the fluxes of water, energy, solute measured today, those fluxes to the records of those fluxes in the past. So water passed through this Earth material, leaving behind these layers, and so that record that is left behind, we want to be able to relate that to the fluxes we can measure today. And again, another piece of the complexity, however, is we want to do it at all different places on the planet. And the conceptual model for the CZO network would be critical zone observatories, shown here as little cubes, that were arrayed across gradients and environmental variables. So different lithologies, different climate, different topography or relief or uplift rate, different types of biota, human disturbance. And if we could really array a large CZO network like this and understand how the different critical zone systems were functioning as a function of these variables, that would be where we want to be. That's where we want to go. So in 2007, these were the first 3 CZOs that were funded. And then in 2008, 3 more were added. And then, as Enriqueta explained, by 2013, we were up to 10 CZOs shown here in the U.S. Now, in addition, as Enriqueta already mentioned, there's also a growing international network. The word critical zone or phrase critical zone is used now around many scientists. Critical Zone Observatory is used around the world by many scientists. And you can see some of the efforts that are growing in terms of these observatories. And what we are really hoping to do is foster international interactions and learning across the different CZOs and across the different networks. And one way we're doing this is a new Science Across Virtual Institutes, which is a new NSF funding to foster international science among the CZOs. Now, we would like to think about the network of CZOs that we have right now and place them into some kind of network diagram, and this is not that easy to do. Quick and dirty way of thinking about it. Here's our climate gradient and our lithology gradient. You can see different kinds of lithologies that are represented. For example, Susquehanna Shale Hills CZO is right here, and you can find we have several CZOs along granite from the Keio in the tropics to Southern Sierra, for example. And then some of the other boxes are from either our international CZOs or some of the CZOs actually have subsites, like our CZO has some subsites on shale that cross the climate gradient. Tim White has worked to build something called SiteSeeker, which you can find on czen.org. And what he's been trying to do with this is think about how this network really allows us to explore all the different variables and think about how we can find sites for particular variables. So just kind of in closing, we see the CZO network as an audacious experiment to use the critical zone as a time telescope. We want to be able to measure water, energy, solute, and sediment fluxes today. We want to look at their record in the past, and then use that as a way of developing models that can project the future, and I like to call those earth-casting models. So the network itself, it includes people, ideas, data, tools, and models, and we're driven by hypotheses, and you'll be hearing about questions of hypotheses from Bill. I think it's useful to think about what we're doing and some of the tensions involved. We are CZOs that were proposed by different principal investigators to do individual science. So we have scientists at each CZO that are pursuing their own science, but we also are trying to bring in new scientists into each CZO. We do science and research, but we also do monitoring. So we collect data over time. And in that respect, CZO Network is a facility that will remain in place for perhaps longer periods of time than some average CZO NSF grants. We're both individual sites, and so each CZO acts individually, but we also act as a network. And we have cross-cutting questions, but we also compete with different ideas and approaches. And so there are tensions, and these are dynamic tensions that characterize the network. So this is how I like to think of it, the science of CZO research. We start out with questions about how systems work. We gather data. We have model development, testing, and refinement. And then with that, deeper process-specific understanding happens, and this happens at each CZO. But then as we learn to data share, and I've already made the point that it's very difficult to data share because the complexity of the data is very high, and those shared data can then be used in development. And that is now where we are now, where we are starting and cross-discipline hypotheses and questions that are emerging, and drives more data gathering with the ultimate hope a really deeper system-level understanding will emerge. And it really is a process that we're moving, and we need help, especially, I mean, now that these CZOs have been defined, we need especially to fill out parts of this diagram. We need people that want to come in and work. So just my final two slides, surface fluxes today. We're learning to read the cumulative effect of those fluxes over time. And then we want to earth cast forward. And with human scenarios of human behavior and with such deeper understanding in earth casting models, we should be able to project what will happen to the Earth surface system tomorrow. So that's sort of the mission and vision as we see it. Okay, so I think I'm going to stop sharing. And I hand it over to Bill.
Good morning, all. My task here is to tell you about the common questions, and I think the best way to do that, particularly since we're inviting people to join us, is for you to get a brief overview of what these observatories are, because to some degree the questions we address reflect where we work, and where we choose to work reflect the questions we're asking. So I'm going to first tell you about, briefly, one slide each, about each of the observatories, and I think you'll see, and I've created a kind of gradation, not in time, but on similarity of questions, that I think shows you the spectrum of approaches and the similarity and the range in which these CZOs are approaching the problem of the critical zone. So we'll start with the Shale Hills, and the stated hypothesis there. We see the image, the LiDAR shaded relief topography of the site, is to project the critical zone evolution, into the future, and it requires knowledge of the geological history, observations of critical areas of human activities tomorrow in this site in Pennsylvania. And there's a nice diagram groups put together to sort of show the conceptualization from, this is very important, reading the record, how it informs what the measurement influences the measurements of today, and then how to conceive of what will be coming in the Anthropocene. You see the through-going theme here of the past to the present to the future, and the evolution of the critical zone affecting how it will be in the future. The second slide is bolder, and there's a certain similarity to this. You'll see the panel there showing the range of sites, so it's a different approach. It's a large gradient from the flatlands into the mountains, and here their aim is to focus on the architectural evolution. So here's the cartoon of the critical zone over time, how it conditions hydrologic and biogeochemical response to ecosystem structure, and how it responds to future changes. You see a similar theme here, architecture. That's the structure as illustrated here in this diagram, and how that architecture affects and is affected by the processes, and then how will things change in the future. And so you'll see they'll document critical zone architecture, denudation processes, weathering fronts, hydrated biogeochemical coupling. Southern Sierra, the key hypothesis there is to predict how water budgets and vegetation will respond to climate warming, land management disturbance, and it's crucial to understand how vegetation, long-term climate, and parent material jointly regulate. And here I've emphasized the coevolution of regulative properties in ecosystem structure and function. So again, there's this sense of the coevolution of the critical zone and ecosystem function. And here in the Southern Sierra, they exploit the climate gradient caused by an elevation gradient. So you'll see over here going from lowland oak savanna to upland subalpine, and looking at the state of the critical zone in each one of these, from vegetation down to the bottom of the critical zone, and then pondering, importantly, as climate warming comes to California, how will the vegetation hydrologic system adjust, and will it progress up into these different critical zones, or can these higher critical zones take the vegetation that is seeking new environments as climate changes? Another, and the next slide I'll mention, is the Santa Catalina Mountains and Jemez River Basin CZO. Their key question is, how does variability in climate, lithology, and disturbance influence the critical zone structure and function over both short and long timescales? So again, you see here the sense of the structure and function of the critical zone, but here the key word is the variability and short and long term. Here too, the critical zone is exploiting a climatic gradient associated with an elevation gradient, in which there is both an elevation gradient and varying lithology from granitic and schist to up to rhyolite, with an interest in the effect of fire. And here is an illustration of how this group is considering the interactions of surface water dynamics, subsurface biogeochemistry, landscape evolution, ecohydrology toward water, carbon, and weathering fluxes. You can see kind of another one of these conceptual diagrams of the kind more that Sue laid out more specifically for this site. The Eel CZO asks the question, do specific locations or time periods of significant activity disproportionately impact weathering, biogeochemical cycling, hydrologic processes, atmospheric inputs that drive landscape evolution and CZ function? So I've emphasized, I think the key attribute here is the idea of events at specific locations and time periods having a consequence for how the critical zone operates. And so on the left here are key words out of 4 statements about this critical zone. The idea that there's transition this landscape is going through transitions, nick points propagating through the landscape, changing how this critical zone works. That this is associated with local intense biochemical reactions, that there's local sediment production, and then there's the challenge of bringing up all these, assembling all these localized effects into a scaled up view. So you can see kind of a transition here to the evolution over the long time scale and the coevolution to now looking at the local variability and a local event having a consequence for the large scale, as sort of illustrated here by a drawing from Jane Willebring of an incision into a weathered landscape. At the Eel River, the goal is through intensive field monitoring of the critical zone, is the idea that the critical zone mediates watershed currencies. So this is a very much looking outward from the critical zone and asking how it affects water, solutes, gases, sediment, biota, energy, and momentum. As that material passes through a subsurface environment and microbial ecosystem into the terrestrial ecosystem, up into the atmosphere, out through diverse drainage channel networks in which aquatic ecosystems interact with currencies, mediating the delivery of nutrients to coastal ecosystems. So this critical zone, which is illustrated in a LiDAR image at the top and a cartoon below that sort of shows the structure of the site where there's intensive monitoring, is more focused on the critical zone as a mediator of processes and a little bit less on the actual evolution. And to ask these questions, though, does lithology control rock moisture availability of plants and therefore overall resilience of vegetation to climate change in seasonally dry environments? Might that be so? How are solute and gas effluents from hill slopes influenced by biota and changing moisture regimes? What controls the spatial extent of wetted channels in the channel networks of seasonally dry environments? And will changes in critical zone currencies induce climate or land use change, or induced by climate or land use change lead to threshold type switches in river and coastal systems? So the transition here in sort of perspective is now we're thinking of the critical zone as its influence on the atmosphere, its influence on the amount of water in channels, that influence on ecosystems, and even the influence on the delivery of goods to the coastal network. And with that, all those questions in a changing environment that we're going to experience in California, both from land use activities and from the climate that's about to come. Now, the Reynolds Creek then is very much focused on carbon, on soil carbon storage, flux, and processes. So the key hypothesis is that soil environmental variables, water content, temperature, net water flux, measured and modeled at the PDON and watershed scale will improve understanding of prediction of soil carbon storage and flux and processes. So they're developing a conceptual model and intend to understand the processes to the level of being able to model this and bring in a better understanding of carbon storage, flux, and processes. The Christina River Basin has these hypotheses, two primary ones here back in the East Coast, which is hydrological, geochemical, and biological processes produced and mixed mineral services and organic carbon are rate limiting to watershed scale, chemical weathering, and soil production and carbon sequestration. So there's the idea that the focus on organic carbon and moving up to the watershed scale is similar sort of handshake with the Reynolds Creek effort. And then emphasize here, humans accelerate rates of carbon mineral mixing, resulting in anthropogenic carbon sequestration significant to local, regional, and global budgets. So the focus here, as you can see, we're stepping toward looking at the human influence on the critical zone as a primary interest in this critical zone. And with that,
Bill, I'm going to interrupt you real quick. Sorry, this is Dan. Could everybody, if you're not Bill, please mute your phones right now. We're getting a lot of weird chatter in the background that's distracting. Thank you. Sorry, Bill.
Okay, that's fine. So the Calhoun site is that further emphasis on the human influence, where the Calhoun seeks to understand how the critical zone responds to severe soil erosion and land degradation. And so the key hypothesis that the impressive reforestation mass fundamental alteration of the critical zone hydrology, geomorphology, biology, and biogeochemistry, and then I emphasize here, post-disturbance critical zone evolution may not so much recover as restabilize altered state. So this is, you can see in the photograph, and data the kind of collecting here on chemistry with depth, the idea of an altered system and how it's going to recover and how we might guide that. And then the final critical zone, the 10th one, in this order I've presented, is in definition, intensively managed landscape. So here, the key hypothesis that we've passed a tipping point, there's still a lot of noise back there, resulting from human modification, and has gradually shifted from, and their idea is that pre-human disturbance, there was a system of transformation of nutrient, water, and sediment storage. And with the disturbance, those transformation processes have been altered to being primarily a transporter out of nutrients, water, and sediment storage. There's still someone else talking in the background?
Bill, let's just listen who's on the phone or listening in on this. You've got to mute. You're ruining the presentation. Mute.
Okay. I will continue. So the perspective here in the Minnesota River, Clear Creek, Sangamon River, then of a transformed system, that one is in disequilibrium, and that there is how to tackle this problem of how it operates and how it will operate in the future. So I think you see in this ride then of the 10 CZOs there's a shared set of questions about how the critical zone operates, but a varying emphasis from fundamentally the development architecture to fundamentally the influence of humans and how we mediate or direct the future state of the critical zone. So this leads then to the two shared conceptual statements that Sue made, and I'll explain a little bit further, that the critical zone evolves a structure that influences storage and water flux and solutes and sediment gases, biota, and energy. This idea in red evolves a structure. This exists. And then by mediating these stores and fluxes, the critical zone provides ecosystem services, and is thus critical to people. So here I want to emphasize by structure. It generally refers to material properties, vertical and lateral variation, porosity, permeability, fracture characteristics, water retention, density, etc. It includes the mantle of vegetation. And the flux through and out of the critical zone connects it to the atmosphere and the river ecosystems, which it receives drainage. Ecosystem services, a popular term, is considered in these critical zones to include things such as carbon storage, water supply, nutrients, vegetation growth, and functional river and ecosystems. So I think you can see what we mean by these general terms of structure and ecosystem services. And then the three shared questions that are most general is what controls the critical zone properties and processes. I hope you now see from looking at the critical zone hypotheses how central that is. What will be the response to critical zone structure and its storage and flux, climate, and land use change? I think you can also see that. And then finally, how can improved understanding of the critical zone be used to enhance ecosystem services? So the idea then is using intensive field measurements with the observatories will provide the data to guide process understanding to develop models that explain critical zone evolution, to forecast possible future states, and to guide land use decisions. All of the CZOs have modeling components through a wide range of approaches. Now, if we go back through each of those CZOs and call out questions that are narrower than the ones that I presented to you per CZO, we would come up with something like 21 sub-questions. I'm not going to march you through them. I'm going to give you just 4 that illustrate the nature of question posing, and these are 4 questions that are shared across many of the CZOs. The first one was, how does the critical zone how does critical zone development depend on lithology? I think that's very clearly stated in Sue's example and hinted at in the presentation. And it turns out that the 3 most common lithologies in our CZOs are granitic rocks, shale, and volcanics. There's a redundancy, if you like, in different critical zones on these 3 different rock types. The second is, how does hillslope aspect, as it influences local climate, affect critical zone evolution and structure? And most commonly, we're thinking of the north-south comparison. Dramatic differences in vegetation, local climate, local critical zone properties. It's a natural experiment to connect climate and the critical zone processes. The third is, how do biota influence solutes and gas fluxes in the critical zone? And by and large, we're talking about vegetation and deep microbes. In many of the critical zones, there's interest now in seeing what the microbial community is doing beneath the soil, the processes deep into the critical zone. And then how will critical zone processes mediate the effects of climate change on water resources? And to a large degree, this one takes a highlighted interest toward the west, where we have recurring and expanding drought, and we have the periodic fires, and how the critical zone is going to mediate these effects. Now, for these common questions, there are also common modeling components needed, which a model, in a sense, is a question. How do I model a certain process? And so at the bottom here is listed a bunch of acronyms, some which are familiar to you and some which may not, that deal with watershed level, catchment level, hydrologic, geochemical processes. I'm going to give examples and more specific components of any model that are a focus of various groups in the CZOs. The understanding of fracture flow and rock moisture dynamics in hydrologic models, linking the vegetation species to the critical zone properties, linking the critical zone to atmospheric processes, linking water runoff from the critical zone to flow in rivers, reactive transport modeling in the critical zone development, and the landscape evolution modeling, including the effects of critical zone. So each of these six models, each of these six have models of various kinds being developed within and discussed across the various CZOs. And then what we've done in doing this is kind of we identify questions, we have models that are assisting in the development of questions, and then we have these kind of themes groups that capture these questions into just working groups that are emerging from discussion of the critical zones. And there's one is focused on what controls the processes and the properties, and this has been one focal question is what sets the depth of fresh bedrock under a critical zone. This is a shared interest across most of the CZOs. Modeling climate and fluxes in the critical zone is another working group. Critical zone controls and solute concentration river discharge, that linkage between the critical zone and wetland streams. The critical zone control and water availability to plants, organic matter in the critical zone, biogeochemical processes in the critical zone, iron mobilization and precipitation in the critical zone, the use of isotopes to track processes and rates in the critical zone, ecosystem services provided by the critical zone and international critical zone. So that, oops, I didn't mean to go that fast. Let me just go back to that last statement. There we go. So what you can see in this this presentation then is, in summary, the 10 critical zones that they provide. They each are stimulated by individually generated hypotheses and questions, but across them you see a similarity of questions about the structure and process of the critical zone, the processes that operate and are mediated by the properties of the critical zone themselves, and then how that provides ecosystem services. We have specific questions shared across the critical zone. We have working groups that are then chewing on an aspect of that. There are then active modeling to explore and share across the critical zone. So I'll stop there.
Thanks, Bill. So you should stop sharing your screen, and John, you should get ready.
Where is Adobe Connect? There it is.
Okay, my name's Jon Chorover, and I'm going to pick up where Bill left off. And the focus of my portion of this webinar is on common measurements. And I just want to lay a little bit of the context out for this up front, in that, as Sue highlighted early on, each CZO proposal had and was developed with a unique set of hypotheses and experimental designs. That said, and these were done essentially independent of each other. That said, there was an overarching goal that the network really be greater than the sum of its parts, and that there be opportunities for interaction among the CZOs to test mechanisms that went beyond the individual CZOs. So there are mechanisms to achieve this, including the questions, the working groups, the campaigns and modeling that Bill discussed earlier. And another is through a subset of common measurements. And these common measurements would enable testing of new hypotheses, existing hypotheses across a wider class, just in a CZO, by taking advantage of the full group of observatories. A way to look at that large view the precipitation space of the CZOs, and you can see that there's a wide range in annual precipitation from the hot, dry southwestern U.S., southern Sierra, to higher rainfall in the Eel River CZO, and then eventually you get out here on the East Coast precipitation regimes in the Shale Hills and Calhoun, and the highest precipitation, of course, in Luquillo. So there's an opportunity for looking at critical zone architecture, dynamics, and evolution across a wide space in climate space that crosses, in some cases, a variety of different lithologies, but in some cases, constant as well. As pointed out, there's a lot of granitic sites in the observatory network. So all the CZOs seek to develop a common set of measurements, and when we say common, referring to the fact that there are a subset of measurements that all the CZOs are interested in pursuing. Of course, there's a subset of measurements that individual CZOs are pursuing that won't necessarily be common with others, or maybe common with one or two, but there will be a set of measurements that we're trying to collect across a wide range of the observatory network. And so these measurements pertain either to architecture, and architecture refers to three-dimensional components, and it includes bedrock, soil, vegetation, and topography distribution, as well as chemical depletions and enrichments, and the zonation of microorganisms as a function of depth and lateral distributions, and ultimately the development of hydrologic porosity and flow paths. And then the CZOs measuring critical zone dynamics, which are different, of course, than architecture, which takes relatively long time scales to develop. Critical zone dynamics refer really to event-based and continuous fluxes of water, energy, solutes, gases, etc., across interfaces, including the land-atmosphere interface or bedrock saprolite interface. And we're all interested in measuring storage and budgets of water, carbon, lithogenic elements at a variety of scales, including the catchment scale. I want to emphasize, of course, that critical zone research translates across a wide range of space, from molecular scale all the way up to watershed or catchment scale. And ultimately, we want to be architecture to dynamics, and the way that we're doing that is through developing models of understanding critical zone evolution, and these are processed timescales much longer than the afforded by a Critical Zone Observatory grant, and that require, therefore, some between models that help to simulate regolith and drainage valley formation, bedrock fracturing, soil production, geochemical changes, etc. And so in the next few slides, I just want to highlight some examples of what these common measurements are by giving examples from the individual CZOs. I'm not going to show slides that show the same data from all the different CZOs, as that would take too long to go through, but I just want to show some examples of common data sets that all the observatories have agreed to use in a variety of ways to address both their individual hypotheses and the collective sort of cross-CZO questions that are emerging and that Bill highlighted. So probably one of the primary data sets that all of the CZOs are using and have acquired or are in the process of acquiring is LIDAR, light detection and ranging, which is achieved through the acquisition of aircraft LIDAR data. And one can use those data to characterize the structure of the vegetation canopy that overlies the subsurface, and also to filter out the vegetation, to obtain digital elevation maps of the subsurface. And so a LIDAR example is shown on the left here for the vegetation canopy in a mixed conifer forest site of the Catalina-Jemez CZO on the left. And then algorithms can be developed, for example, on the right, to relate mean canopy height to above ground biomass, which is often an interest to any of the CZOs in terms of characterization of biomass accumulations as a and carbon fluxes and the like. So LIDAR data is one example, in this case also from the Catalina-Jemez, is the characterization of subsurface architecture. Techniques that I'll talk about for that, but one is traditional soil sampling and the acquisition of either soil cores or excavation of soil pits at the top couple of meters in the mobile soil zone above bedrock and fractured bedrock, but where there's a significant amount of biological activity, carbon accumulation, and weathering. And so what's shown here is just for a small 20-hectare catchment in the Santa Catalina Mountains, the collection of data on the physical, chemical, and biological properties of soils that can then be geostatistically interpolated to give maps of critical zone of the zone, so carbon accumulations, clay accumulations, and also lithogenic element depletions and enrichments tend to, in this case, follow hydrologic patterns of development. Another area where there's significant cross-CZO interest is in characterizing microbial community ecology and its variation with depth in soil profiles and in the deep critical zone below the soil zone into bedrock. Here are some data from the Boulder Creek CZO that highlight differences in archaeal and bacterial taxa as a function of depth in the Gordon Gulch catchment. And in this paper, one of the things that was highlighted was that the variation is extremely great in the near surface among different excavated pits or pedons, and that variation in microbial community ecology decreases with depth even in the top 2 meters of the profile, and that at depth, many of the profiles exhibited comparable or very similar microbial ecology, whereas in the near surface, variation was very great. And this variation in the near surface within a single catchment was as great as across 40 different biomes globally sampled. And so, as Bill mentioned, there's an interest in understanding the depth distribution of microbial and how that affects ultimately critical zone development, biological weathering, and things of that sort. Another method that's being used now very commonly across the observatory network is a set of geophysical measurements. So it's really a large array of geophysical measurements, including seismic, seismic refraction, GPR, electrical resistivity tomography, etc. Many of these methods are now being acquired across the CZOs, either individually or in collaboration with the NSF-funded Wyoming Center for Environmental Hydrology and Geophysics, Steve Holbrook et al. And here are some data from the Southern Sierra CZO by Holbrook et al. That are seismic velocity measurements. So the depth of the weathering profile extending well beyond the previous couple of slides, essentially tens of meters in depth down to this 4,000 meter per second velocity contour, which is suggested to be competent bedrock based on bedrock outcrop calibrations. And so there's a growing interest in this deep weathering profile across the CZOs and the use of geophysical methods which are capable of probing that zone that's otherwise very hard to reach, and maybe using some of this geophysical data to understand the porosity distribution of that deep weathering profile and how it may contribute to hydrologic response and things of that sort. Another way, of course, to access the deep critical zone is through deep borehole excavations, and this is another area where the CZOs are collaborating, and these deep borehole excavations can then be used for borehole instrumentations, for well installations, and deep groundwater sampling and temperature gradient measurements, etc. But the borehole data itself, that is the weathered material that's extracted from the borehole, is very useful for geochemical characterizations. And So all of the CZOs are in the process of collaborating essentially on this, what we call Drill the Ridge project, which is essentially a deep drilling set of projects that will allow us to measure the geochemistry of boreholes as a function of depth. So here are some data from the Shale Hills CZO that show depletions. In this case, these are tau plots showing relative chemical depletions or enrichments, in this case of potassium, magnesium, and silicon in boreholes at the Shale Hills Critical Zone Observatory, showing depletion of these lithogenic elements in the near surface going all the way down to 7.5 or 8 meters, which is attributed to the weathering out of that near surface zone of feldspars and illite, and then a return to more like background levels at depth. So again, this deep critical zone is a common area of interest and is therefore the focus of common measurements across the CZO network. Another set of measurements pertain, so all of the previous slides and examples I've shown have really focused on the architecture, that is the structure of the critical zone that forms over relatively long time scales, perhaps aside from the microbial ecology, which is maybe much more quickly evolving. However, the next set of measurements pertain largely to the dynamics, and in this case, all the a variety of dynamics in respect to fluxes. In particular, one of the most important fluxes, of course, being the water balance, the flux of water through the critical zone. And here's some work from CZO from a recent paper by Goulden and Bales that shows how the precipitation tends to increase with elevation in the Sierra Nevada due to orogenic effects on precipitation. Evapotranspiration tends to increase with precipitation up to a point, but then decrease because of biological activity. And runoff, essentially the difference between precipitation and ET, tends to increase thereafter. And so the water balance is captured here through the use of eddy flux towers, which many of the CZOs have installed, and other methods of precipitation and runoff, basically hydrometric measurements in these catchments. And so capturing the water balance is one of the common measurements being pursued by all of the CZOs to be able to get an understanding of through flux of water, which is key to development of the architecture of the critical zone over long times. Another example of dynamics is the variation of microbial activity, not just composition, but actually the activity of microbes with depth. What's shown here is extracellular enzyme CZO, and the large decrease in extracellular enzyme activity derived in nitrogen and phosphorus hydrolyzing enzymes. And that can be explained in large part by the decrease in labile carbon. One normalizes to the carbon available attack, one sees straight lines and a loss of that exponential decrease in activity. So expectations for what at deeper depths in the critical zone are that some of these enzyme activities might decrease as a result of diminished labile organic carbon, but at this point, very few of the CZOs have actually made those measurements to determine that. Another area where all the CZOs are collecting common measurements pertains to aqueous geochemistry and sediment transport. Again, this is dynamics types of measurements that help us to understand the response of geochemical fluxes and or sediment fluxes to hydrologic events. So here are some groundwater well data for geochemistry from the Eel River CZO showing that with increasing elevation of the groundwater table, that is in response to hydrologic events, the rise of the groundwater table towards the surface, we see many of the non-hydrolyzing base cations at different downslope, midslope, and upslope positions. And so there is essentially a concentration-discharge relationship that's embedded in these data. There's also important concentration-discharge relationships embedded in these data from the intensively managed landscape CZO in the Midwest, where many of the landscapes are agricultural, and where we see with increasing at the flume CZOs, there's a significant increase which is important because of potential issues related to topsoil erosion and just sediment transport off-site and erosive fluxes in the critical zone. So very highly responsive sediment flux to hydrologic response in these catchments. And again, both the geochemical types of measurements that are depicted here and the sediment flux measurements that are depicted here are part of this sort of dynamic component that's being measured by the CZOs. In fact, if we catalog the sets of measurements of the different CZOs and depict them in this way, in this matrix where we label the 10 CZOs across the top and the different types of measurements that are being made, both dynamics and architectural type measurements down this axis, looking at land change, vegetation and microbiota, structural and dynamics, soil or vado zone measurements, saprolite and bedrock, surface water dynamics. And we have all of the CZOs indicate where they are making measurements along these, with these different types of components. We see that there is already established a wide set of common measurements across the CZOs. The Z's in this case indicate where some of this is through collaboration or these are planned measurements coming in the near term. And what we see in general is that we're already in measurements. This is not to say that we're all making these measurements in exactly the same way. The plans for these measurements were developed individually, but what we are doing now is communicating across the CZOs to try to enhance cross-comparability of the measurements being made and using shared technologies and shared approaches as much as possible. So what we're hoping, I forgot about that next part, what we're hoping is that we can eventually develop where, for example, one could come over one of these, let's say, soil physical and textural characterization and click on a box here for bring up a map showing where these types of measurements CZO, so that folks both within other CZOs and outside in the community, outside the CZO group, would be able to determine where be of use to them in their work. So finally, I wanted to emphasize again that common measurements are focusing really on dynamics type measurements, and these are measurements of processes that occur over short time scales, and also of architecture, which forms, and essentially we're sampling a snapshot in time, the current state of the critical zone, and it's formed over long time scales. And what we're interested in is linking those two through the process of critical zone evolution that's often addressed through modeling approaches to understand linkages between dynamics and architecture. We need to understand how the forcings associated with dynamics lead to different types of architecture. And ultimately, different architectures buffer the critical zone system to affect dynamics as well. So with that, I'll close and I'll close out my presentation and hand it back to Tim.
Yikes. Thanks, Jon.
Yes.
I'm wondering, would you mind commenting just briefly while we get organized for some, would you mind commenting briefly on the breakout groups from the Tenaya meeting and maybe how that feeds into the common measurements effort?
Yeah, sure. So there was a meeting that Tim's referring to that was meetings. As Enriqueta pointed out, we have CZO all-hands meetings every 2 years. There was one held at the Southern Sierra CZO. And as part of those all-hands meetings, we try to really enable greater collaboration among the different CZOs through having breakout sessions where individuals from each of the CZOs collaborate or get together and develop ideas cross-CZO collaboration. And several of those were mentioned in Bill's talk. He showed a slide, the working groups that are currently structured for the CZO. These working groups evolve, and then they dissipate when the projects that are being done are completing, and then they form again sort of organically, and we encourage that, of course. I mean, this is something that we really want to see more of, and several of these working groups developed some goals and objectives for the upcoming year, including workshops and developing intercomparisons of data sets. So just to give one example, I'm leading a cross-CZO working group on concentration discharge relationships in catchments of the CZO observatories. And what we're interested in doing is bringing together essentially data that relate solute concentrations in surface waters emanating from the critical zone in our different sites to discharge values, and to try to understand how that can help to inform us about the composition of the critical zone and the hydrologic functioning of those sites. And there are several other working groups that are actively involved in addressing issues such as the depth of regolith, that is how deep does the weathering profile go before you reach competent and essentially low permeability bedrock. Another is focused on organic matter dynamics and what controls the stabilization of organic matter in the critical zone. Others are focused on biogeochemical hotspots and their evolution in the critical zone. And there are several others as well. And so one of the slides that Bill showed highlighted those working groups, and what I don't know if it's currently the case, but those working groups should probably be posted on the website so that folks that are interested in participating in a given working group that may not have attended that meeting could participate, could get involved. Does that answer your question, Tim?
Yeah, that was perfect. Thanks. Enriqueta.
Yes, I'm here.
I wonder, do you have any additional comments from the NSF perspective on common measurements?
No, I think that I'd like to know whether there are any questions for NSF from the audience.
Yeah. So let's see. We're beginning to get some questions. I see one from a PhD student wondering where I can find more about the general things that I need to know before I start working on a dissertation. Well, I'll answer that one. Go to criticalzone.org. That's a good place to spend several hours learning about the generalities of critical zone science and the observatories.
If I can add, there are about 1,000 publications in the website that you can access that have been produced by the large team.
And yeah, the only other thing to add too is that if you go to the website, you can actually search for publications and individuals working at the CZOs by sort of disciplinary area. So ecohydrology is one of those disciplinary areas, and you could actually find publications from the CZOs that pertain to ecohydrology that way.
I saw Gwen McPherson. Oh, here we go. So let's see. Is there any kind of policy related to legacy ownership of the data so that the subtleties associated with data collection and analysis can be communicated to potential users and data generators or collaborators on cross-disciplinary projects? Does anybody want to comment on that one?
I can comment on it. I don't know if I can answer it. This is Sue. Hello, Gwen.
Hello.
I think that the metadata explains a lot of the subtleties, if not all the subtleties in data collection. And that's why I was making such an emphasis of the fact that the data structure and cyber infrastructure for data is so complex, because you not only have the data, but you also have to have the metadata about those values. And so Depending on the type data, the cyber infrastructure is either more or less developed. So for LiDAR, I think the data is up and it's, everything you need to know is there with it, I think. And then with the hydrologic data, because Quasi's been building the Hydrologic Information Service, I think there's a lot of metadata that comes with it that's organized. And then when you get to some of the other kinds of data sets, there is no organized way for the metadata to be presented necessarily. And so there's differences from one CZO to the next. And the way I like to think about this is the different disciplines are kind of moving along the track of figuring out what the cyber infrastructure for their data set might look like. But we're also doing this in a coordinated way that Anthony Aufstenkamp at Stroud Water Center is promoting, where they're creating a data structure that would house all these different data sets. But it's very difficult. But if you look online, most of the metadata should be available for the different kinds of data sets to answer your questions. And then if the second part of your question is about co-authorship or sort of who gets to be a collaborator, I think those are usually adjudicated on a case-by-case basis. And I know at our CZO, we've just recently pulled together a document which summarizes best practices, or at least our perception of best practices when it comes to issues around collaboration. But none of those are very easy to hammer out because different disciplines, again, approach that differently. So it's a little bit difficult, and it's variable depending on sort of a case-by-case basis kind of thing that happens.
Thanks, Sue. Bill Dietrich. Bill?
Yes, I'm here.
Oh, hi, Bill. Hey, I wonder, would you be willing to share some thoughts on moving forward? I mean, you came in new to the observatory program and immediately embarked on a pretty ambitious and awesome effort to, put together that list of common science questions. And I'm just wondering if you have, a vision for moving that list down the line.
I'm not yet sure what you're asking. What does down the line mean? Help me. Maybe I need more tea. What do you mean?
Help us continue to progress.
Oh, I see it as in taking a couple different paths. One is the working groups taking the working groups tend not to be focused around a particular question, but the working groups are about one or more of the questions, and I think the working groups can have the coagulating effect of getting across CZO conversations on common questions happening more. And so the one that we've talked the most about is, and we've reduced it to the statement of drill the ridge, the idea of characterizing the critical zone down to, let's say, fresh bedrock in a variety of locations in a similar geomorphic context to look at lithologic, climatic, and other controls is something that we've had workshops about and are developing. I think that the other exercise that's still underway is just really understanding what, for me, has been grasping what each observatory's characteristics are, and so we can begin to more fully grasp what our range of opportunities are in terms of materials, climate, topography, erosion rates. This is still something I think that at least I'm trying to help put together and grasp so that we see what we have is kind of already a layout of observations that provide information along a gradient about these basic questions that develop. So I see this the attempt questions, 21 questions, how you want to count them. to now, talking specifically about we saw come out of the all hands meeting, I would say a recognizable set of theme groups that the question. So I see I would say a dynamic between the questions and the activity, and I suspect and I would want and hope that new questions will emerge as people. I think that the Sierra was a great. There was a great sense of cross CZO activity that I think will cause us to even further refine our questions.
Thanks, Bill. Enriqueta, I'm putting you on the spot again, and just wondering if you could share any of the specifics about the development of a potential international.
Before that, I wanted to kind of throw out a question. Is it possible to actually have the working groups in such a way that there will be like a place that people go to a website and see what the activities of the work they want to get involved? Is there, Tim, what do you know about that? Is there a possibility for that to be posted so that the updates and the meetings and the reports will be available to anyone that will want to, of course, asking permission, will want to be part of it?
Well, currently we don't have anything like that set up, but the plan is to, once we sort out what we're going to do with criticalzone.org and czen.org, is to make something available on one or the other or both.
This is Sue.
Yeah.
This is Sue. One of the working groups that didn't really meet at the last all hands because of time constraints, but is actually functioning, is CZTOPE, which is a group of people really interested in using isotopes, all different isotopes, on a small number of samples from the same spot. So sort of like shining 15 different flashlights on the same elephant in the dark room. In other words, 15 different isotopes. And so CZTOPE as a group is being promoted by Jason Austin, Grit Steinhoffel, and Pam Sullivan. And then I think they're at Duke, here at Penn State, and at University of Kansas. And they just started a group called CZTOPE on czen.org, but it was just started this morning. So that, I mean, that's the we're play around with, trying to keep a site open and updated with information. And so people could, Pam Sullivan at University of Kansas, if they wanted to be a member of that group and see what's going on.
Okay, great. So the question was about what may be happening in the international arena. I think the internet has a lot of potential right now because there is a great interest from a number of contacts work together with the US CZOs and the other CZOs that have been formed, and so we are planning on a conversation that will take place at the AGU meeting, and then see what would be the nature of the collaboration, what makes sense at this time to propose for making opportunities available. It will be interesting to receive opinions or suggestions from the community of listeners as to what they think are possibilities out there. But we have some ideas based on conversations that have taken place in the past. So I would say that this conversation that we're going to have is between the France, UK, and the United States, but there are also interest in other places like Australia, and I forget the list, but maybe Tim can add to it. But there are other countries who are which are interested, and also the European Union. They have been a project going on for a number of years now, and those are that. So I think this is an area that is going to grow, and there's going to be much more potential for collaboration. And as Sue mentioned, there is a SAVI award that is going to be focusing on creating international and national partnerships. So more of this is to come.
Thanks. We just got two questions. One of them is about the availability of the webinar, and I'll answer that quickly and say it's been recorded, and we'll put a link to it on criticalzone.org. The second question, it looks like, Enriqueta, I think this is for you.
Okay.
It says, although a call for proposals is not planned in the near future, is there a long-term prognosis for the CZO program? Is 10 the maximum number of sites planned?
Oh, well, this is a hard question to answer if you want a definite answer. I think that the availability of funds will determine how many sites will eventually be, and the opportunities to be able to support other sites. I will also say that there is opportunity to be an affiliate with the CZO. So there may be a site that already exists in another form and wants to become part of the CZOs. There's always a possibility of applying for funds to NSF to support an activity that will not be of the same level as the CZO, which right now are receiving $1 million per year. But the program will entertain any proposal that would like to leverage what is now in existence. And so what the future is going to be looking like is it all depends on budget. And 10 is not the absolute number.
Thank you. Are there any other questions? It's 12:30, which was the scheduled ending time for today, but we could take another question if there's one that comes up immediately. Otherwise, thank you for participating, and note those activities and events at AGU and come to our town hall. I think that's it. I'm seeing a lot of thanks for a webinar. So let's call it quits for today and see everyone at AGU.
Very much to everyone. This is Enriqueta.
Goodbye.
Bye.